Let's look at this next objective, the Pythagorean theorem. Remember again, this course is in the context of everyday life. We just saw how we could apply volume to everyday life. How will the Pythagorean theorem apply in everyday life? Well, before we do some applications, let's just recall the formula. Pythagorean theorem is for a right triangle. Right triangle means there's a 90-degree angle. You have two legs, we call those A and B, and then the side across from your right angle is always called the hypotenuse. It doesn't matter which leg is A, which leg is B, it's just that the two legs are attached to the 90-degree angle, and across from the 90 degree is the hypotenuse. So I'm sure the formula's somewhat familiar. A squared plus B squared equals C squared. So you square leg A, you add that to squaring leg B, and you will always get the square of side C, the hypotenuse. So I've got three applications here dealing with the Pythagorean theorem. Got some missing sides that we want to find. So why don't you pause the video, work on finding the missing values, and then check your work. The first three problems involve using the Pythagorean theorem. Basically three right-degree triangles, 90-degree triangles. The value of x, the missing value of x, in the first example comes up to be 10. Because there are squares involved, we have to take the square root of both sides to solve for a missing side. So you'll notice that I had to take the square root of both sides here. The square root of 100 gave me the 10. Side y, which is a leg, in the next figure turns out to be 5. You can see my work here. I had to square root both sides, and the square root of 25 was 5. And then the figure with the ladder up against the wall. The foot of the ladder, the base of the ladder is 35 feet from the wall. The length of the ladder is 50. 50 is your hypotenuse. It's side C. 35 is a leg, and we're trying to find the height, which is a leg. So 35 squared plus h squared is equal to 50 squared. We have to square root both sides. And these little wiggly lines, I'm not using equals, I'm using approximation, approximately equal to, because I did some rounding. So h is approximately equal to 35.7, and in this case it would be feet. We can't forget to put our unit. Okay, last part on the Pythagorean theorem, is 8, 15, 7 a Pythagorean triple? What a Pythagorean triple is the first value is a leg, the second value is a leg, the third value represents your hypotenuse. So the question is, would these three numbers work as a Pythagorean triple? A, B, and C. Well, if you check it out, all we need to do is figure out, is 8 squared plus 15 squared equal to 17 squared? So there's a question right here. We don't know. Why don't you figure it out? So did you figure out that it is indeed a Pythagorean triple? 8 squared plus 15 squared is indeed equal to 17 squared. So that is a Pythagorean triple. Finally, the last thing we're going to work on is similar triangles, I believe. Yep, similar figures, similar triangles. Triangles are similar if their corresponding or matching angles are congruent, they're equal in measure, and the ratio of their corresponding sides are in proportion. There's many types of problems that involve similar triangles. Here's what we mean as far as the definition goes. Here's what we mean when we say similar figures. So let's suppose I have a right triangle that looks like this, okay? And I have another right triangle, but it's sort of a blown up version, okay? Their angles are congruent, and that means these angles here, the corresponding angles, are the same measure. Let me fix that. Along with the 90 degree. And so that's what it means by congruent. The angles have the same measure, and the ratio of their corresponding sides are in proportion. So let me put some numbers on this. So suppose the sides on my small right triangle, the legs were 3 and 4, and the hypotenuse was 5. The similar triangle is a blown up version of that, and it has sides 6, 8, and 10. Well, the sides are in proportion when they're similar figures, and what that means is if you take, let me switch this to a different color here. Okay, let's say I'm going to take this side 6, that corresponds to this side 3. What it means by the fact that they are in proportion is every ratio I create will have the same value. 6 divided by 3 is in proportion with 10 and 5, so I could say 10 divided by 5. Those two are corresponding sides. And then the next set would be 8 divided by 4. If all of these ratios give you the same value, then the corresponding sides are in proportion. Well, 6 divided by 3 is 2, 10 divided by 5 is 2, and 8 divided by 4 is 2. So they're all in proportion. So given what I just did, the previous slide, I've got two similar triangles. We've got corresponding sides. What side corresponds to 40? Well, the side with 4 corresponds to 40. So I would have a ratio of 40 over 4. Which one corresponds to 5? And notice the 5 is in the denominator here. So I'm looking at the smaller triangle, and I see that the 50 corresponds to it. When you set up these proportions or these ratios, you have to compare them in the same order. So I've got the large compared to the large compared to the small. So what would be the numerator for the fraction over here at the end to show the ratio where the denominator is 6? Well, 6 corresponds to 60. If I divided all of those out, I would get the same value, so that tells me that these are similar figures. And we can use that concept to find some missing sides. So take a second, use the concept of setting up those proportions, those ratios, to find side A and side B. Well, given these two figures, I can set up ratios. Side A is to side 15, they correspond. Side 8 is to side 12. Side B is to side 18. So I can set up all these ratios, and I know that they all have to be equal to each other. So I need to pick a set of fractions, ratios, that's going to allow me to solve for one of the variables. So I'm going to pick this ratio up front, A is to 15, as 8 is to 12, and I'm going to solve that. Oops, I didn't want to do that. I'm going to solve that by cross multiplying because it creates a proportion. So 12 times A is a 12A. 15 times 8 is going to be 120, is that right? Yeah, okay. So if 12a is equal to 120, I can divide by 12 to get the value of a, and 120 divided by 12 would be, what would that be? 10. Yes. So side A is equal to 10. I also need to find side B. I need to set up a proportion, pick two fractions so that I can solve for B. So I'm going to pick the ratios 8 is to 12 as B is to 18. I got to make sure that I only have one variable in my setup that I'm solving for. So that's why I choose that one, those two. So we can cross multiply because this turns into a proportion. And I get 18 times 8, I think it's 144, is equal to 12 times B. And if I divide both sides by 12, I get side B is equal to 12. Whoops. So here, side B is equal to 12. Now you can check to make sure your work is correct by putting the value of A right here, which was 10, and the value of B right here, which was 12, and see if all of these fractions have the same value. 10 over 15, well, if I divide them by 5, that reduces to 2/3. 8 over 12, if I divide them by 4, that reduces to 2/3. And 12 over 18, if I divide them by 6, that reduces to 2/3. So all those sides are in proportion. Last example, we've got a figure, and we're doing some comparison. And so we want to set up two ratios corresponding to this proportion that has a missing part. So it says we're taking the side or the piece QL. QL is right here. And we're saying QL corresponds to PM as SQ corresponds to what? Well, the only thing it can correspond to is what's on the other side, that corresponding position, and it has to be JP. So now you're at a point where you can go to my math lab and work on that geometry homework.